When you look through the raw visual feed of a robot moving through a warehouse, you do not see boxes or aisles. You see a chaotic, blurry array of flashing, unstructured pixels. To a machine, a camera is not an eye, it is merely a sensor catching light. Capturing that array of light and storing the pixel values is computationally cheap. The engineering challenge is extracting physical, actionable meaning from that digital noise in real time. This highlights the divide between the hardware that sees and the hardware that moves. Cameras collect passive, two-dimensional grids of light. Physical robotic actuators require precise, low-latency, three-dimensional coordinate commands to navigate space. This gap creates the perception bottleneck. Transforming a raw, high-resolution video feed into physical movement requires massive computational weight. If the processing is too slow, the resulting latency means the robot will crash before it finishes calculating what it is looking at. Overcoming this bottleneck involves engineering a high-speed mathematical bridge capable of translating unstructured light into precise physical action. Two open-source frameworks provide the necessary infrastructure for this bridge: the Robot Operating System, or ROS, and OpenCV. OpenCV acts as the primary image processing suite. It executes the complex matrix transformations and filtering algorithms required to make sense of raw pixel data. ROS serves as the communication and messaging layer. It routes the process data from OpenCV across a distributed network of software nodes to trigger the robot's physical actuators. To understand how these systems interact, we can look at the architectural blueprint developed by Royal Research for robotic perception. The Royal Research model maps out a sequential, three-tier computational hierarchy. A raw image must pass through object detection, then recognition, and finally interpretation. Executing this specific three-tier ROS and OpenCV pipeline provides the technical structure for modern autonomous machines. We can observe this pipeline in a physical case study, a complex, active warehouse floor. The process begins with image acquisition. The moment the robot's camera captures a frame, it generates a computationally heavy two-dimensional matrix of light intensities. This diagram shows the ROS computation graph. The system takes the matrix from the camera node, packaging it into the standardized sensor_MSGs/image data type. This format allows massive visual files to move smoothly between software nodes, flowing directly to the OpenCV node for pre-processing. Feeding raw, full-color camera feeds directly into detection algorithms is inefficient. Processing millions of distinct color values per frame would severely slow the system's critical reaction time. OpenCV executes mandatory pre-processing to mitigate this. It instantly converts the full-color feed into a simplified grayscale matrix and applies preliminary edge detection algorithms. Edge detection mathematically targets areas of high contrast to strip away pixel noise, like surface textures. What remains is a wireframe of structural geometric outlines. Acquisition and pre-processing are exercises in data reduction. The system discards visual noise until it reaches the underlying mathematically useful geometry. With the image simplified, we reach the first tier of the Royal Research framework, object detection. Object detection is the process of identifying regions of interest within the pixel matrix. At this stage, the system identifies that an object exists, but not its identity. Here, OpenCV uses pre-trained models called HAR cascades. The algorithm scans the image for specific contrast patterns. When it finds a match, it draws a bounding box. Within that box, the robot knows an anomaly exists, but remains blind to its specific identity. To classify the object, the pipeline moves to the second tier, object recognition. This requires feature extraction. One efficient method provided by OpenCV is ORB. Inside the bounding box, the ORB algorithm extracts highly unique geometric points, like corners and sharp angles, generating a digital fingerprint. The system cross-references this fingerprint against a database until it finds a statistical match, identifying the geometry of a forklift. For higher accuracy, engineers can integrate deep learning frameworks like TensorFlow directly into OpenCV for semantic segmentation. While detection identifies the presence of an object, recognition confirms its identity. This transforms a pixel cluster into a classified entity. We now reach the final tier of the Royal Research framework, interpretation. Interpretation is where the system maps a recognized object to a physical operational context. Logic maps recognized objects to physical actions. The robot interprets these boxes as inventory to move, while triggering an avoidance protocol for the passing forklift. This final interpretation dictates which ROS message types are published to the robot's motor control nodes. However, this pipeline faces physical constraints, most notably unpredictable lighting on the warehouse floor. Shadows or glare can destroy the contrast profiles needed for HAR cascades or orb feature extraction. OpenCV addresses this with software solutions like adaptive thresholding and histogram equalization. These tools mathematically normalize lighting variances to stabilize visual data. Autonomous systems function by mapping these classified objects to their operational roles, while mathematically correcting environmental noise. When viewed at scale, we see an entire autonomous ecosystem functioning without the limitations of the perception bottleneck. OpenCV provides the mathematical toolset for extraction, while ROS provides the infrastructure to translate those mathematics into spatial navigation. This architecture, as outlined in the Royal Research Guide, is a unified perception-to-action pipeline. The industry is currently expanding these capabilities by injecting deep learning models directly into this pipeline. This integration allows robots to generalize their perception across different settings, from complex healthcare facilities to open-field agriculture. Regardless of the complexity of the AI models, the requirement of moving structured visual data across distributed nodes remains constant. The ability to translate raw pixels into distributed motor protocols is the primary objective for intelligent robotic perception.